If no, then let's go ahead. Why Bandgap materials? I uploaded some paper. They are pretty very what is called important paper, right? Many people refers to this. The first two paper is about gallium nitride. The last paper is about the general ultra wide bandgap device. Okay, right? Have some idea, at least some reasonable idea. Now let's go to more math now, right? Last time we talked about Johnson figures of merit. It is about the power device for RF. Right. If you remember, I say that it's a trade-off between two things. Do you remember what is the trade-off that we care about for the power device in RF?
Frequency and breakdown voltage.
Frequency versus breakdown, very good, right? So why we care about this? Just always think about the base station, okay? Your cell phone base station. They need to supply very high power to you. So they need to sustain high voltage because you need to apply high voltage in order to get high power at off state, okay? And of course, for cell phone, talking about 5G, 6G, maybe even 7G in the future, if there is, then you need frequency, right? That is a trade-off. But why there's a trade-off? And that is here what Johnson figures of merit talking about. So let's just thinking about pure device, right? I write it nice like a resistor. But the point is apply a voltage on top of it, V, and if the length is L, right? So what is the maximum voltage I can apply? It will be L times EC, where EC is the critical electric field to break down. Right? You start applying a voltage, you get certain electric field. You keep increasing your voltage, you keep increasing. Eventually, the field is very large. This can be a PN junction, right? Like, for example, PN junction. Eventually, right, you are going to break it. Right? But on average, it's about the length of the, I should not say PN junction, it's just the length of interest inside a device. For example, this drift region is the length that we are interested in, right? Of course, the maximum electric field is not just V divided by L, but here we assume it is uniform. Then what is the maximum frequency? We know that maximum frequency is just 1/2 pi tau. And what is tau? Tau is the so-called transit frequency. I mean transit time. If you want your signal to respond, you need to let the electron to go from, right? Electron from one end to another. It takes time. If your electron can go there in no time, then you can go with very high frequency. If your electron needs time to get in and get out, then your frequency is smaller. And by definition, the frequency is 1/pi tau. If you have a very small transit time, it means you can operate at higher frequency, right? But how fast can an electron go through? It's just the length divided by the saturation velocity, right? So electron is here and travel at saturation velocity. Then the time is L divided by V set. Is that okay? Now, so we want to find a figures of merit that we have both high frequency and also high breakdown voltage, right? Because if you give me a device, say, well, it has very high frequency, 1 terahertz, but you break down at 0.1 volt, no use. If say you have a very high breakdown voltage, 1000 kilowatt, but your frequency is like 1 hertz, no use to me neither, right? I want to find something for RF, have a good trade-off between frequency and breakdown. So I want to see both of these figures. So by definition, the Johnson figures of merit is VM times FT. But this definition has some meaning because now if you plug in VM is L EC, right? Maximum voltage is length times the critical electric field. And FT is 2 pi tau, 1 over 2 pi tau, right? Now, but our goal is what? We don't want the L, we don't want the L because this is depends on the device. We want to look at the material property. Okay, so based on this, what's L? L is tau times V set, right? Based on this equation, L times, right? And then you have EC divided by 2 pi tau. So it is saturation velocity times EC divided by 2 pi. So this is the Johnson figures of merit. So how do I evaluate a material, whether it's better than the other? I look at its saturation velocity and it's the critical electric field. Okay, their product is the Johnson figures of merit. If I have high saturation velocity, I also have high critical electric field, then I have a good device. Let's look at our device here. Critical electric field is related to the band gap. So ultra-wide bandgap definitely will have better critical electric field. But then we also need to look at the mobility. It is not here. So the best one, I think probably is diamond or gallium nitride. Yeah, somehow we did not put mobility here. Okay. Any question about the Johnson figures of merit? Right. After all, our goal is to have trade-off between frequency and breakdown. So now you probably understand why we don't use silicon for the base station. We use gallium arsenide, which has a little bit higher breakdown field and also much higher saturation velocity. But now we are moving to gallium nitride, which has very high critical field. Saturation velocity is also higher than silicon. Right? So I can do 6G or 5G more easily with gallium nitride. For silicon, no way. No way for 6G, I guess, in my opinion. Maybe I'm wrong. Right? But for 5G, maybe okay. Is this okay? Any questions? Now then we go to another figures of Baliga. This is related to regular power device, right? Can someone again tell me what are we trying to optimize? What are the trade-off for Baliga figures of merit you try to look at? Johnson figures of merit is for RF breakdown versus frequency. This is what? For a regular power device. Or can you guess? What are we trying to optimize? And this is what we have been talking about so far.
Breakdown voltage and resistance.
Thank you. That is what we have been talking. Okay, R on. Okay. Again, if I have very big breakdown voltage, I will have a very small R on. That would be great. And you can think that, oh, then maybe Baliga figures of merit is something like BV over R on. Makes sense, right? But if you remember what we learned last time, is actually BV squared over R on. So why is that? Because we want to represent it in the fundamental parameter. Now let's see why this is the case. Let's just look at a Schottky diode. In this Schottky diode, this is in the reverse bias, right? And this is, okay. So first I want to find the for reverse bias, maybe let me finish this. At reverse bias, you actually have a triangular electric field. Okay, well, if it is lightly doped. So, okay, you have triangular if drift region is lightly doped, right? So I assume you know about this already. If not, you can solve the Poisson equation, okay? And I don't require you to solve that, right? Maybe next time I should ask you to do this in the homework. Maybe this time we can do it in the homework. You try to solve for this triangular electric field. You see that when the doping is not too high, you get a triangular shape. Now you think about that, you keep increasing the breakdown voltage. Electric field will increase. Where would it break down? Is it going to break down at this point, or this point? Is it going to have impact ionization at which point first? Do you break down a high electric field or low electric field?
High.
So which point will break down first?
The
A, B, C.
C.
C will break down first. C is here, right? C breakdowns. Right? So what we care is to see what is EM. I don't care what value here because the first point going to break down is EM. Okay? So let's do it step by step, right? Let's try to, thank you. Yeah, Elisa. Now, let's try to first look at the R on. What is R on? R on, of course, is just equal to, if
area into
say again.
area into
Great. Area time resistivity divided by length. Correct?
Yes.
No, sorry, opposite. This is the conductivity. Should be length divided by area, right? Larger area, smaller R on. I know what you all know that, but I just put it in the wrong direction, right? But do you remember what I care is not area. I care I care is not R on, it's R on specific. So I care about this quantity, rho times L. Okay, now maybe, sorry, let me call this W instead of L. Okay, W. Is that okay up to here? But what is rho? Rho, you need to go back to review your, or we did that earlier. It's just equal to electron constant Q charge times electron concentration times mobility. That is rho. It's 1 over Q and mu, right? If you have larger N, larger mobility, then 1 over it will give you smaller resistivity, right? So just a reminder, rho equal to 1 over sigma. This is resistivity equals to 1 over conductivity. Okay? And conductivity is Q and mu, right? This one, I assume you know that already. Or what is the concentration of the electron? It's just equal to the doping IF, Na, or let me call it Nd. Right? Whatever I dope here, 1e17, I get 1e17 of electron. Okay, so this is the first equation. R on specific resistance equal to this one. Okay? Any questions about how we derive the specific on resistance? Now then I want to look at what is the breakdown voltage. If you use Poisson equation, right? You will find that because this is a, do I spell it right? Maybe no I. Poison. Maybe I spell it wrong, sorry. Right. So if you remember that this is a triangular field, your integral of the electric field is equal to the potential drop, right? So the voltage equal to half of the width, right? This I call it width also, times EM. Are you okay with this? Times E, yeah, let me call it EM. Or let me E at X equal to 0. For the electric field at 0, this is triangle. You integrate is just half of this width times EM. That is the voltage across. Is this okay? But at breakdown, right? At breakdown, we have E at X equals 0 equal to EM, critical electric field. We also have V equals to the breakdown voltage. This is the voltage we say it just breakdown. And one more thing we have, this is W equal to WD. That you just extend the depletion width to reach here. Because you can make the drift region even larger, but then you waste that area. So you want to design a drift region such that the W equal to WD. Okay, so with this, then what do you get? BV equal to half WD and EM, right? So let me call this WD also. So maybe I should not introduce a new variable, right? It's just the width. I just call this WD everywhere. So later you won't get into trouble, right? So what does it mean? It means the WD equals to 2BV divided by EM. Okay, but do you remember what is WD? This is a depletion, right? So we just use the depletion equation, 2 epsilon times the BV divided by Q and D. Do you remember? I'm going to erase it, but do you remember at that time we say the depletion width of transistor is 2 epsilon 2 phi s if it is in inversion divided by Q and D, something like that? Here, the potential across is the BV, not 2 phi s. Okay, that's why this equation is the same if you try to do an integration. Okay, and then now I can plug in. So first of all, I actually should label this one as number 2. Okay, and then with this one, I get Q and D equals to 2 epsilon BV divided by WD squared. Okay, and then you try to evaluate this quantity, BV squared divided by R on. You substitute them, right? I'm not going to show the step. You will get 4 divided by epsilon mu divided by EC cube. And this is the Baliga figures of merit. So now you see why I have the BV square. Because by using BV square, I only have the intrinsic property of my material, the critical electric field, the mobility there. Right? I know this is a little bit lengthy, but I want you to, let me summarize one more time. You have a Schottky diode. We know that it's going to form a triangular electric field just by solving Poisson equation. And our goal is to say that what is the merits that I can use to describe how good my material is. We try to have trade-off between BV and R on. So we say that what if we have a drift width of WD? Then it will be rho WD divided by A as the on resistance, but we need specific on resistance as we said last time. So after the derivation, we get the specific on resistance as this one. And then we want to try to see how about the BV so that we can relate both of these equations to the fundamental parameter. We say this is a triangular so that the voltage across it is half the width times the peak electric field, right? And we also want to make it so that when it breaks down, this depletion width just touch the end. Why is that? Because if your depletion width is longer than that, when you break down, it just touch here. By making it longer, it won't increase the breakdown electric field, but your drift resistance is going to increase. So this is not an optimal design. An optimal design must be when it breaks down, the electric field just touch this point, right? So we just use the equation we learned before, including how to find the depletion width, right? And this is just the Gauss equation, Gauss law here. And then from this equation, we get QD equal to this. Now we just need to substitute WD into here, and then QND into here. Then after some manipulation, you will get this Baliga figures of merit. You're not required to know how to derive this, but you're required to understand what we are doing. For example, why we need to find the on resistance, why we need to find the breakdown electric field, because we care about this trade-off. And on resistance depends on what? Depends on doping and the length. Breakdown depends on what? It depends on the critical electric field, EM, right? And finally, you see Baliga figures of merit is BV squared divided by R on. It only depends on these material parameters. And now you see that if I then increase my critical effective electric field by 10 times, I increase my Baliga figures of merit by 1,000 times. Critical electric field is related to the band gap. I told you that it's about square relationship. So think about this. I increase my band gap from silicon to gallium oxide, to gallium nitride by about 3 times. So my critical electric field increased by 6 times. So my Baliga figures of merit is going to increase by 6 to the power 3. Of course, we need to think about mobility and epsilon also. Is this okay? Any questions? I know it's a little bit messy, but any questions? Okay, yeah. So there's a question about epsilon. Yes. What is the epsilon here, right? You're right. It should be the whole thing, right? This means epsilon 0 epsilon r. Yeah. Okay, so I think it's still confusing, but just let me know if you have a question. We can discuss more, right? It's difficult to talk about this topic. Now, finally, let's go to gallium nitride, right? We have covered silicon carbide, gallium oxide, now gallium nitride. Gallium nitride is very important. And this is the last thing I will cover, right? Diamond and aluminum nitride are not that important at this moment. You see, this is, what do you call? Hexagonal structure. Remember hexagonal structure, we have so-called silicon phase, carbon phase in silicon carbide. In gallium nitride, you also have gallium phase